Welcome to the session 18 of Operating System and Linux. I'm Manibhushan D'Souza, and in today's class we are going to look at classical problem of synchronization. There are many problems that are associated with the synchronization. These problems have to do it with the concurrency control, how to control the concurrency. So the problem is given, and then you are asked to find the solution for that particular problem. In particular, this problem involves the problem of concurrency control. Okay, these particular problems, even though they look very funny, but they are used for testing the newly proposed synchronization algorithms. So whenever a new algorithm is created, or whenever a new synchronization scheme is generated, these problems are used to just to test whether those particular new algorithm are able to solve these classical problem. So now let's look at the classical problem. The first problem about the classical problem is the bounded buffer problem, which you have already seen. Now, why do we have to use this bounded buffer problem? Now, this will test the power of synchronization. So, it is going to tell you whether your algorithm that you have proposed is it able to provide a better synchronization. Now, what is there in a bounded buffer problem? We know very well in a bounded buffer problem we have a producer which produces the item, and we have a buffer that can contain up to n number of items, and there is a consumer who is going to consume the items produced by the producer, and the capacity of this buffer that we are talking about is en. So there is a bound on the capacity of this particular buffer. Okay, how to solve the concurrency problem? Now, what is this concurrency problem? The concurrency problem here is the consumer has to wait until an item is produced. The next one is the producer has to wait if the buffer is full, and there must be a way in which the items which are produced by the producer, before it is put into the buffer, the consumer cannot access it. In other words, when the producer produces an item and puts it onto the buffer, the consumer, at the same time, the consumer is not allowed to access it. The same way, when the consumer is accessing an item, the producer has to be prevented from putting a new item into the buffer. In other words, there must be a mutual exclusion. So either a producer puts an item into the buffer, or a consumer removes an item from the buffer. So how to solve this particular thing? We use semaphore. In the last session we have seen a semaphore is nothing but a simple integer variable which has two functions. One is the weight and the other one is the signal. Weight is going to reduce the value of the integer, and the signal is going to increase it. Now in this case also we are going to use a mutex, which is a semaphore, to achieve the mutual exclusion. In this case, we initialize the mutex with the value 1. So we start with the value 1. There will be two other variables. So one variable that we are going to use is the mutex, that will be used for achieving the mutual exclusion. There will be two other variables. One is the empty, other one is the full, that indicates the state of the buffer. So if empty equal to some value, then you can take some action. If full is some value, you can take an action. In the initial state, okay, in the initial state, the buffer is completely empty. So if the size of this buffer is n, so initially when you start the process, the buffer is empty. So what will be the value of the empty? Empty will be equal to n. That means to say that there are n empty slots are available for the producer to produce an item and put them into this vacant n items, so a vacant place. In the beginning, the buffer has no items. So what is the full status of the buffer? Full status of the buffer will be 0 because there is no item that is produced. Suppose if one of the item is produced by the buffer, so what will be the value of the full? Value of the full will be 1 because one item has been produced. What will be the value of empty? Empty will be n minus 1 because one slot has been utilized. Suppose if the second item is produced, what will be the value of the full? There are two slots which are full, so the full will be 2. How many slots are empty now? N minus 2 slots will be empty. So this is how the empty and full is being used up. So let's look at the solution over here. So there will be a semaphore. Remember, all of them, full, empty, mutex, are all semaphore. Again, let me emphasize again, semaphore has only two methods. One is wait, other one is signal. When you call wait, the value of the integer variable is reduced, and when you call signal, value is increased. However, all the operations are performed in a single unit, so it has to be performed in a single unit. We initialize the full with 0, as I told you, empty with the 1, n, and the mutex with the 1. So let's look at the algorithm over here. So we will look at the algorithm from the point of view of the producer. So what the producer will do? Producer will produce a item. And what the producer must do now? Producer has produced an item. So the producer now has to put this item onto the buffer. So what the producer will do now? So the producer has to prevent the consumers from accessing the buffer. So what the producer has to do? First, the producer, there are two things the producer has to do. One is the producer has to prevent the consumers from accessing the buffer. The next one is producer can put an item into the buffer only if there is a vacant space that is available. So if there are no vacant space available, the producer cannot put an item. Suppose if the entire block or if the entire buffer is full, even if the producer has produced a new item, the producer cannot put it onto the buffer because the buffer is already full. So the first thing the producer has to check is whether there is an empty slot where the producer can produce where a producer can put an item. So the producer is going to call on the wait on empty. So what is the initial value of empty? So you know, I've already told you, empty, there will be initially there will be n slots which are empty. Initially all of them are empty. When you call wait on empty, what will happen? So let's recall what will happen on the semaphore. Semaphore is yes. So what will happen if yes is not equal to 0 or less than or equal to 0, then what you will do? F is not equal to, remember, you will reduce the value of yes. That is what you've seen it in the semaphore. So if the value of yes is not less than or equal to 0, you reduce it. This n value is not less than or equal to 0. So what will happen when you call on empty? When you call on empty, n value will be reduced to n minus 1. Suppose if n equal to 5, suppose if there are 5 elements are there, when you call wait on empty, what will be the value of n? N value will be 4 because s minus minus will reduce the value of n by 1. So that is what is going to happen. What is the logical significance of this? Logical significance of this is if you are able to reduce one number from 5 to 4 if you are able to do it. That means to say that there is one empty slots that is available. So there is an empty slot, that is why you are able to do it. Suppose if there are no empty slots, what is the meaning of this? If the empty is 0, then you will not be able to add a new item because there are no empty slots. So you know very well in the semaphore what will happen. If the value of s is less than or equal to 0, you will have to wait. You will go for a busy wait. So that is what happens. So assume that initially n is equal to 5. So he is able to reduce producer is able to reduce it. So the producer is going to come over here. Now what is this mutex? Mutex is used to, mutex is a, by the way, mutex is a short form for mutual exclusion. I will make it as exclusion. Now somehow my caps lock is on, that's why everything is coming in the that one. Okay, so it's mutual exclusion, short form for mutual. So it is a short form for mutual, exclusion, MUT. Let's say again I pressed caps lock. Let's say MUT exclusion, mutual exclusion. So that's a word that is being used. So what is the meaning of saying this is, so if the slot is empty, if you are able to get one slot as an empty slot, then what you must do is the producer has to produce the producer has already produced an item. Producer has to place this item, and when the producer is placing the item, he has to prevent all these consumers from accessing the buffer. So in other words, he has to lock the buffer. How he can lock the buffer? He will say mutex. What was the initial value of the mutex, by the way? Did you remember that? So mutex was initially, mutex was 1. So if you call wait on mutex, what will happen? Mutex minus minus, yes, minus minus. So in this case, mutex minus minus. So what will be the value of mutex? Mutex will be 0. Next one, whoever comes up to here, even though the slots may be there, so when the one producer goes here, the next producer may come. No doubt they can come. They will see that okay, the number of slots are 4, so that means 4 empty places available. Well and good, 4 is there. But what is the problem over here? This person, the first producer, has locked it, so the buffer will not be available for the others. So you lock the buffer and then insert your items that you have produced into the buffer. Once you have successfully placed your item, unlock it so that others can enter. How do you unlock it? You call, so remember, when you lock it, the mutex will be 0. Then you call signal on mutex. What will happen? Mutex will be 1. So what is the meaning of 1? 1 means that if anybody is waiting over here, they can enter. So if it was 0, anybody who was waiting here, they can't enter. You just signal it so that others can enter it. Next one, what you must do, you have produced an item. Now empty is reduced. What will happen to the full? So what, there is one other thing that you have to, two variables were there. What is full? Full is initially it was 0. Now one item has been produced. In other words, whatever value that was there, if 3 items were produced, the full will be 4. So how can I increase the value of a full? You just call signal. You know very well, when you call the signal, it is yes plus plus. You know very well. So when you call wait, it is yes minus minus. When you call signal, it is yes plus plus. So one item will be produced. So now let's look at the consumer's point of view. So you have a buffer here with the n number of slots, and you have a consumer who is consuming the item, who is supposed to consume the item. What are the things that we have to take care over here? The first and foremost thing, consumer can consume only if there is at least one item that is full. So if there is only one item is filled, or if full is at least one, then the consumer can consume it. If the producer has not produced any item, then the consumer cannot consume anything. So the first one is, consumer has to wait until there are some item. In other words, the full that we are talking about, if full is 0, that means no items are there, it is not even full, then consumer has to wait. If full is 1, then the consumer can proceed. But what is the next thing the consumer must do? If the consumer finds that there is one item, then the consumer must prevent all the others from accessing it. How can the consumer do that thing? They use the mutex. So the first thing is you wait on full. So initially wait will be 0, full will be 0. Remember, full is initialized to 0. So if the consumer comes, immediately call for it. What will happen? You know very well what is wait. Wait is if yes is less than or equal to 0, you wait. Otherwise you reduce the value of yes. In this case, yes is equal to 0. Remember, I'm talking about yes in the sense semaphore. So semaphore is 0, value 0, then you will have to indefinitely wait here. If suppose consumer, the producer has produced one item, then what will happen? It will go to the next one and yes becomes a 0, or in other words, consumer becomes 0. So that means you have taken one item, consumer has taken one item. If any other consumer comes immediately, once this item is taken, if any other consumer comes, they will have to wait because until the producer produces a item. So it is simple as that. So one item is produced, one consumer has taken it. What will happen to the next consumer? If the next consumer comes here, that consumer has to wait. Okay, so that's the idea. Next one is on the mutex. You know very well what is the next thing. Suppose if you are able to take one item, what's the next thing you must do? You have to lock this buffer. How can I lock this buffer? Remember, initial value of mutex was 1. So you wait. So what will be the value of this? It will be 0. So let's assume that there are two items which are produced. So let's come back to the buffer here. So you have the buffer, two items are produced. Let's assume that two items are produced. So what will be the value of a full? I'll take a shortcut here. Full is equal to 2. F means full. The first consumer comes here, he looks at, he or she will look at here and say, okay, I can take the item. So he comes to here, he or she will come here. At this wait, what will happen? The full value is reduced to 1. Second consumer, immediately the second consumer will come. He will look at full, okay, full is 1. Last item is there, I am going to jump and take it. So what will happen? This value will become a 0. The third consumer comes. Third consumer comes and this checks, okay, sorry, there are no more items are available, so I will have to wait. So third one will wait there. Okay, so now let's again come back to the same old story of the consumer. There is a buffer and there are two items that are produced, and what will be the value of a full? In this case, the full will be 2. The first one will come here, he will reduce the value to 0. So sorry, not to 0. So first one will reduce the value to 1, and the second consumer, immediately second consumer will jump, and when the second comes, when she takes it, this value is going to be 0. However, what the first consumer will do then? The first consumer will go to this step. When the second consumer is taking this, first consumer goes to this step. When the consumer goes to this step, what the consumer will do? Consumer will change. Assume that M is for mutex. The consumer first consumer will change the value of mutex from 0. From 1 to 0. In other words, consumer will lock this whole thing. So what will happen to the second consumer? Second consumer will also come to this line, but when she comes to this line, he finds that it is already locked. I can't do anything. Even though one item is there, I can't do anything because it's already locked. So how long the second consumer has to wait? The second consumer has to wait until this mutex is released by calling the signal. So when the first consumer will release it, after removing the item, the consumer will say, okay, my work is over, I will release the lock. Then the second consumer will again lock it. So second consumer will again lock it. Remember, when you say mute signal, it's this value is going to become 1 for the first consumer. Second consumer will come, it will again make it as 0. In other words, she will lock this one, and again will remove the item. What about the empty? Remember, what is the signal empty? Remember, there were two items were there. There were two items were there initially. So let me change the color. Okay, there were two items where the f is equal to 2. You remember that. First item will first consumer will reduce it to 1. So what will happen to the empty value? Whatever that empty was there, empty has to be increased by 1. That's simple as that. So that is what you are doing here. You are signaling the empty at the end, saying that one slot is empty so that producer can produce an item and place it there. Okay, so this is the one of the problem, bounded buffer. Let's look at the second problem. The second problem is regarding the reader writers problem. So in this particular scenario, we have a data object. It could be a file, it could be a record, it could be a memory location, anything. So there are several types of concurrent processes who want to use that particular resource. Either it could be a file, it could be a record, it could be anything. So there are many who are interested in that particular data. However, there are two categories of processes are there. Some of the processor just wants to read it. The other processor wants to update it. So there are two distinct type of processes are there. So some of them are only interested in reading the content. They will not make changes to the content. So those are called as readers. So who are readers? Who are only interested in reading the content. They will not make any changes. So if you get a notes, where you go to the library, you buy a book, you read that book, you return that book, somebody else will take the book and read it, somebody else will take it and read it. So they are all readers. Okay, when you go to the examination or during the beginning of the year, they will put your register numbers. So during the examination, they will put the hall ticket, the hall number, allocate the rooms for you. So they will write your register number. You read your register number. Your friend will also read the register number, their register number. They don't need to read the same register number. So during the nowadays, because everything is coming in the mobile, but in olden days, at least during the SSLC, your results were displayed on the notice board. You see your result, your friend has on their result. If two people see the same content, nothing is going to happen. It's not going to erase the content. So when you are reading, nothing is going to happen. So if 10 people are simultaneously reading, so during very well, if you travel in bus and other thing, so one person will be carrying a newspaper, all the 10 others will read from the same newspaper. So when they read from the newspaper, nothing is going to happen. So if there are 100 readers are there, or 1000 readers are there, or n numbers of readers are there simultaneously doing something, nothing is going to happen. Reading will not create a problem, but writing will create a problem. If one of them writes it, then the problem will come. What will happen? So let's assume that, so this is your one page. So a reader starts reading from here. So the reader has started reading from here, here. So reader is in this place, but writer was there. The writer changes the value here. So what happened? Reader has already read a wrong value. So for example, the question was answer any one from the 5. So that was the question. So question is given as answer any one from the 5. So you are given 5 questions. From there you have to pick only one. You are so happy. So you have read it, but somebody came and say that answer any 4 out of 5. Change it. You don't know. So right at the top, somebody has made it answer any 4 out of 5. But you didn't know that. You read it as answer any 1 out of 5. You wrote the answer for one question. You came out of the examination. But what will be the consequence? Then you know very well. So you are supposed to write 4 questions. You wrote only 1. three questions you have not attempted, so you know what's going to happen. So what happens is, when a reader is reading, if a writer goes and updates it, it's going to create a chaos. Okay, so when a reader is reading, if other readers are also reading, then there is no problem. So if two readers are reading, there is no problem at all, because they are not changing the value. If one reader is reading and then one writer is coming and making changes in the beginning, then there is going to be uncertainty. So which one is correct, which one is wrong? You might have taken this value and you may be adding, suddenly those values have changed, then you have to redo the entire calculation. So this is going to create a problem. So if there is one writer, then readers are not allowed, also other writers are also not allowed. You can't have two people trying to make changes, then again it will be a problem. So if there is n number of readers, there is no problem. But if there is at least one writer, all the readers are out, all the writers are out, only one is allowed to go for. Let's so look at this particular scenario, where here the question is or the scenario is slightly different. Okay, so what must be done in this case is, to maintain the consistency, writer must have an exclusive access to the shared object. Okay, so this particular synchronization problem, that's why it's called as the readers writers problem. Okay, there are many solutions that are available. I will show you only one of them, and this is called as first reader writers problem. So first readers, that means readers are given preference, writers are not given preference. So first readers, then if the time is there, writers are allowed to write. So when the process starts, writer comes first and say, okay, wait, there are readers are there, let them complete. First preference is given to readers, writers can come later. So what will happen is, in this case, no readers will be kept waiting. So when the reader comes, so you are always welcome, come read and go. But when the writer comes, if there is any reader, you tell the writer, you wait, let the readers go out and then you do it. Okay, so what will happen in this case, it may so happen that a writer, you may say wait, and when the writer comes, okay, one reader was there, so you say one reader is there, you don't go. So writer will wait again. When the second reader will come, well, first has not completed, second reader will come, so you welcome second reader, you allow. So the writer will come again and say, can I go now? You say, no, you can't, because two readers are there. Okay, writer will say, I will wait. After some time, three will come, readers will come. So you are giving preference to readers. So what will happen? Writer will wait, and they may starve to death. So you know what is the meaning of saying starve? Writer is hungry, he wants to write, he or she wants to write, you don't allow them to write. He wants to write again, you are not allowing. Finally what will happen? There is, you are not giving the resource. If you don't give water, what will happen? People will die of thirst. If you don't give food, people will die of hunger. Similarly, you don't allow the writer to complete their process. What will happen? Finally, operating system will tell the writer, you are taking so much of time, what are you doing? You please come out, I will not allow you to execute. So the writer process itself is killed. So writer will die of starvation. So this is called as starvation to death. Okay, so now let's look at the solution for this one. How do you go about it? Okay, so we need a few things over here. First one, we need mutex. Remember, why do we use mutex? To lock something so that others will not touch that. So mutex is like a lock, you lock it, once your work is there done, you unlock it. So that's the one thing. The other one is, because you are giving the preference to the readers, you must know how many readers are there. So that is the one, the important thing. At a time, how many readers are there? Because you can allow any numbers of readers, so read count will be there, and you can allow only one writer at a time. So only one writer preference is there. So if one writer is writing, reader comes running, so can I go? No, you cannot. If the control is given to writer, reader has to wait. Remember, once the control is given to the writer, readers has to wait. You can't allow the readers to read. No, you can't say the writer has completed the 10th pages, you start reading from the first page. No, it is not allowed. So when the writer is there, no readers are allowed. So you have one other mutex for writer, so WRT. So initially you are not locking, you are allowing the writer, so both are true. So mutex is 1 initialized, writer is initialized 1, and there are no readers, that's why you are doing it. So when the library opens, so no morning, nobody is there, so count of readers are 0. So you get 0 there. Let's look at how the process will go. So read count will keep track of how many processes are reading. Okay, mutex will ensure that there is a mutual exclusion, okay, whenever the reader is updating. Okay, the write functions as a mutual exclusion for the writers. So when one is writing, remember the write value was 1 initialized. Even though I have not told you many things about it, remember I was only talking about one writer. There can be many writers, then allow only one writer to write. If you allow two writers to write, then they will, one will write, other will erase it, other will update it, and they will quarrel each other, nothing is going to happen. So this is the two things. Few things you must note. What are the few things? Remember, in this case, when a reader is there, writer is not allowed to enter. So that means the first reader to enter. So if there is a library, the first reader who enters it, he or she will put a board outside, notice outside, no writers are welcome. So writers, please go out. So don't come. So in other words, when the first reader enters, the first reader has to do something, do some trick, play some trick, so that the writer will not enter. So even if one reader is there, writers can't enter. So the first reader who enters, he will put a board outside the library or outside the resource saying that writers are not welcome. So writers cannot enter. The last reader, remember there can be a number of readers, so they will read and they will complete and go. Okay, they will, you won't sleep in library. You go to library, you read, and then you walk out. So when you walk out, the count will decrease. Okay, initially count is 0 because nobody was there in the library. The first person comes, the reader count will become 1, then the reader count will become 2, 3, 4, 5, and so on. Then one person will start walking out of the library. So from the 10, 8, 9 and 10, 9, 8, 7 and so on, it will start decreasing. The last reader, the last one to go out of the library, has to remove that board. Why has to remove the board? Because there are no readers are there. He or she is the last person to walk out. So when that person is the last person to walk out, when no readers are there, there is no problem for the writers. Writer can go. So the last person who walks out of the reading process will allow the writer to enter. So the first person will block the writers, the last person will allow the writer. So let's look at this particular algorithm. So in this algorithm we have semaphore for mutex and write. Also we have a read count which is initialized to 0, no readers are there, only one writer can write at a time, and mutex is 1, that means the lock is open. Now let's look at what the writer is going to do. Remember, a writer can write only if the write is active. So if write is 1, what will happen? If WRT is 1, when you call wait, what will happen? This value will become 0. That means no others will be allowed. So when the first writer comes here, initialized value of writer was 1. So when you call wait on WRT is 1. Remember, initial value of WRT is 1. So when you call wait, what will happen? Yes minus minus. Remember that, yes minus minus. In the semaphore, it is minus minus. If it is greater than 0, minus minus. So yes becomes 0. Next writer comes or next anybody comes, they cannot enter because the value is 0. So in the other words, the first one who goes, he will lock it, will lock the entire library. The writer enters, he will lock the entire library. No readers, no writer, nothing. He or she is the only one person. So locks it, writes whatever changes that are required, and finally unlocks it. Signal, what is signal? S plus plus. Remember, in the semaphore, one is S minus minus, other one is S plus plus. So S plus plus means right, plus plus means 0 plus 1 is 1. So unlocked it. So it's simple as that. What about readers? So first one, reader, there are if you look at here, there are two sections are there. So there are two places where the readers are locking. This is one lock, wait and signal. Look at this, is one lock, wait and signal. Wait means you are locking it, signal means you are unlocking it. On the mutex, remember, wait, lock it, signal, unlock it. Again, wait, lock it, signal, unlock it. So this whole thing has to be done in a single slot. So when this step is performed, no others will be disturbing the reader. When this step is performed, no others will disturb the readers. So let's look at the first reader who is going to enter. The first reader who is going to enter will lock it, so that others will not come and disturb. Increase the count. What was the initial value of a read count? A read count was initially 0. So read count was 0. So read count plus plus means it is 1. Okay. Then if the read count is 1, he is going to wait the writer. Now what is the meaning of saying wait for the writer? What was the initial value of writer? Initial value of writer was 1. If you call wait on WRT, what will happen? S minus minus. In semaphore, minus minus, that means it's going to be 0. What is the significance of this? Significance of this is you don't allow any writers to enter. So that is what I told you. The first one to enter will put a board outside the library saying that the writers are not welcome. So this is the step. So here you are blocking all the writers from coming here. Who is going to do this? The first one. The first who comes is the one who is going to do it. So his or her work is over, they will unlock it. Why they have to unlock it? Their work is over, so they have entered. Others can come. Who is that others? Who is that others? Other readers. Any number of readers can come. So one person comes. When you go to the library, you write on there will be a register. You write on the register. Then do you wait there only? You go out so that others can write it. So similarly, you increase the counter, you go out and start reading it. But if you are the first person, you are supposed to put a board outside the library saying that no writers are allowed. Okay, that's it. So you read the entire book, then you walk out. So when you walk out, what you must do in library, I have not every library, in some of the library, when you walk out also you have to put a signature. They will take the reference section in particular. We go to the reference section. When you enter, you have to write it. When you come out also, you have to write it. The entry time and coming out time. So when you enter, you wrote it. When you are coming out, again you lock the register so that others will not do it. When you enter, you are increasing. Okay, you are the one. When you are moving out, you are decreasing it. So 5 people were there. You increased it and made it to 6. When you are walking out, how many people must be there? 5 must be there because you are walking out, is it not? So it is count minus minus. So the next one is, if you are the last one to come out of the library, I told you the last reader who walks out will remove that board. What was the board? The first person has put the board. No writers are allowed. If you are the last person to go, you will pull the board out. What is the meaning of saying pull the board out? You will allow the writers to enter. So here, if you are if the count is 0, so you are the last one. No, 0 means what is the meaning of say read count is 0, no readers are there. Then you signal the writer saying that you can do it. You can write it and remove the lock and walk out. So this is how it goes. Let's look at the last one, and this last one is the dining philosopher's problem. So this is a very special problem that is meant for a large concurrency problem. Okay, so here The problem goes like this. We have five philosophers. So one, two, and three, four, five. So you have five philosophers who are sitting on a circular table. Okay, here. Okay, and what they are doing, these philosophers, philosophers are great thinkers. They are thinking. So they think, and when you start thinking, what will happen? You become hungry. When you become hungry, you start eating. So that's it. So these philosophers, he or she, will be thinking, and after thinking, they will become hungry. So when they become hungry, even though it is not shown in this diagram, so there is a ball of rice in the middle of the table. So here there is a ball of rice. So you have full rice that is kept. So what the philosopher will do, one plate is there. The philosopher will take this rice, and they will have to take two chopsticks now. This is a Chinese story, so that is why these chopsticks. You may say that no, why can't you take a spoon and eat? Why? What? How can you eat rice using chopstick? Have you seen that chopstick? These Chinese people use those two sticks. That is that they are using. Now you may say that why can't they use a spoon? So they can use spoon if they are elsewhere. Now assume that they are in China now, or Japan, or any other Taiwan, or any other place where they are using chopstick. Now you know very well, if you want to eat using chopstick, you need two chopsticks. With one stick you can't eat. So what is happening over here is there is one stick on one side. It is shared among these two. There is also one stick that is shared among these two. This is also one philosopher, this is one philosopher, this is one philosopher. So one stick is common between these two, and one stick is common between these two. Now what will happen is the philosopher has to somehow catch hold of both the sticks. If you get one stick, you can't eat. Remember that. Okay, so you need two sticks. So the philosopher has to get both the chopsticks. Once the philosopher gets hold of both the chopsticks, what the philosopher will do, he or she will start eating without leaving the chopstick. He will keep on eating, and once the stomach is full, what the philosopher will do, keep the chopstick outside in the same place, and then start thinking. So because they are philosopher, you see, so they, when they are hungry, they will try to grab the two chopsticks which are nearby. Remember, the philosopher is a very decent person, so they don't go here and then take the chopsticks from here. No, the chopsticks which are there on the left and right side, the nearby chopsticks, so they will try to grab the two chopsticks which are on the left and right side. If they get hold of it, they will start eating without releasing the chopstick. Once they have completed eating, they will again release their chopstick, and this process will continue. Now you may say that, okay, so what is the problem? Why do you do this much of trouble? The problem is, okay, a philosopher can pick up only one chopstick at a time. Okay, and the philosopher requires two chopsticks to eat, and once the philosopher starts eating, he will not release the chopstick, he or she, until the he or she has finished eating. Okay, and then starts thinking it. Okay, now you may say that, okay, what is the problem? What is the problem, sir? Why did you tell that this story to us? This is a heavy synchronization problem. Remember, here the synchronization, the coordination is between many resources, many philosophers. If a philosopher gets only one chopstick, what will happen? The philosopher is already hungry. You are not feeding because the philosopher is not able to catch hold of the other chopstick. Without the two chopstick, the philosopher, he or she can't eat. When they can't eat, they will be hungry, they will starve, and the philosopher will die. So you have to see to it that philosophers don't die. So that's a very important thing. So that's a very so that there is a, this is a large class of a concurrency problem. Okay, what about the other? Look at this scenario, one other scenario. Let me take you back to this one. Now suppose all the five philosophers are hungry at the same time, instantly. So this philosopher will take one, this philosopher will take this one, this philosopher will take this one, this will take this one, and this will take this. What will happen? Everybody has one chopstick. I told you philosopher needs two chopsticks. So one philosopher got one chopstick, and the philosopher is waiting for the other, but other is there with some different philosopher. So what will happen? Everybody is waiting and everybody will die of starvation. So this is called as deadlock. What is deadlock? I will talk about the deadlock story later in the other videos. But in the deadlock, nothing is going to happen. Everybody is stuck. No process is executing because everybody is blocked. Everybody expects the others to do a favorable thing. Now, during the traffic jam, you have seen what happens is you are driving a car or your bike. If you are driving a bike, you can always go from any direction. You can walk out. In India, it is possible. But if you are driving car, it is not possible. So when you are driving these four wheelers, what will happen is these four wheelers you might have seen. They are there. They are occupying some part of the road, but they don't allow others to go. So they expect the who is in front of you has to move first. You are not going to do any sacrifice. So the first who is there in front of you or behind you, they are supposed to do all the sacrifice. So what will happen? Everybody is thinking like that. End result is nobody is moving. So this is the same story. Everybody got one chopstick, and everybody expects the other to release their chopstick. I am not going to release my chopstick because I got one. I want the second one, so let the other person give. So I am not going to give. So what happens? Other person is also thinking like that. I got one. Why should I give? Let the other person leave. So nobody is leaving, and they will all of will die of hunger. So this kind of problem has to be solved. Okay. So what is the solution for that? Again, remember, in order for getting the concurrency, now the problem is who has the problem? It is not the philosopher who has the problem. Problem is there with the chopsticks. Okay, why the problem is there with the chopstick? Because if one person gets the hold of the chopsticks, the other person cannot get that thing. So that is mutual exclusion. Suppose if I lift one chopstick, that's the end of it. Others can't get that same chopstick. So there must be a mutual exclusion. How many sticks are there? If you have counted, 5 philosophers and 5 chopsticks are there. It is not, everybody is not given. If you look at the diagram again, everybody is not given two chopstick. One chopstick is shared among them. So 5 philosophers and 5 chopsticks are there. So what is the problem here? Problem is the chopstick has to be somehow mutually exclusive, has to be given in a mutual exclusive manner to the others. So that is, so how can you do it? And definitely you need many semaphores in this case, because the 5 chopsticks are there, 5 semaphores are required, because every time one chopstick is taken, you have to lock it. You know very well, you use mutex for locking it. Now I can't say mutex and other, so we'll take chopsticks. There are 5 chopsticks are there, and all of them are semaphores, and initially it will be available. So I will take the value, initialize the chopstick as 1. Okay, so how do we go about doing it? So if you get the chopstick, ith chopstick, I is chopstick number 1, chopstick number 2, 3, 4, 5, and so on. So you know very well, this is how the chopsticks are kept now. So this is chopstick number 1, this is chopstick number 2, this is number 3, this is number 4, this is number 5. If you get the ith chopstick, you have to get the ith plus 1 next chopstick. Remember, you can't get I told you already, they are philosophers, they are very decent people, so they don't put their hands on the other side and get this one. So if you are taking the ith one, I plus 1 has to be taken. So you wait on I1, the chopstick I, that means lock the chopstick I and lock the chopstick I plus 1, eat it, release it, and then start thinking. So eat, think, and so on. The full story is not shown over here because it's going to be a complicated algorithm altogether. I will show you the simplest version over here. If you really want to interested in knowing that thing, you have to refer the other books. maybe the latest edition, not the 6th edition, the higher edition you can watch, the newer read, and you will get the real solution for that. Okay, so let's look at the solution for this. Even though this kind of solution, if you lock the chopsticks, definitely you will prevent two from accessing the same chopstick. That's the one you get it. But this will not solve the deadlock problem. What is the deadlock problem? Everybody gets hold of one chopstick and they are waiting for the other. Okay, so there are somehow the chopsticks has to be given in a or distributed in a manner such a way that there is no delay. There are many solutions that were given. I will not go in depth into those solutions because it's going to take too much of time in explaining them. So first one is even though 5 philosophers are there, you tell the philosophers that at a time only 4 philosophers will eat. Others, one philosopher, you sit outside and do whatever thinking you want to do, you do outside. So that is one solution. Okay, the philosopher may not like that thing because they are all respected people. Okay, they're very decent people. So what's the second one is? Second one is you tell the philosopher that okay, you got one chopstick. If you cannot get the next chopstick, you got the right hand side chopstick. If you can't get the left hand side chopstick, then leave the left hand chopstick. So you hold the chopstick only if you are able to grab both of them. If you are able to grab one and if you are not able to grab the second one, leave the first one. So if you are eating, if you want to eat, then get both of them. If you get one and if you get stuck in the second one, you got the first chopstick left hand side. The right hand side chopsticks you can't get it. Release the chopstick that you have taken. Leave it back, give it to the others. So it's a decent way. Okay, philosophers will always agree with that. Okay, you tell the philosopher if you get only one chopstick, if your second one is not available, leave the first one also. Let the others eat and then you can eat. Okay. The other solution is suppose if the philosopher says no, that is not possible, then you go for the other one. You give a numbering. So if the odd number philosopher, you say that you start with the left chopstick first and then take the right chopstick. First left, then the right. The even numbers, take the right first, left. So this way also you can solve the problem. You read the references to know more about it. Okay. Even though all the solutions may give you the solution, the solution may be satisfactory, but they are not free from a deadlock. Okay, so even though what I mean to say is even though they give they prevent you from the deadlock, but they don't prevent you from the starvation. So what is the meaning of that is a deadlock occurs when nobody is able to do anything. Starvation happens is when one of the philosopher, very weak philosopher is there. Let's assume that very weak person is there. Every others are taking, grabbing and eating, grabbing and eating, but this person is not getting because he is weak. He or she is weak. So in that case, one of them may go for the starvation. So that a problem may occur. Okay, that's all in this class. We will meet again in the next session. Again, if you are really interested in the solutions for these problems, please refer the Galvin's book on the operating system concept. Thank you for your interest.